What happens if you fall into a black hole? Would you be stretched, crushed, or erased from existence? Can anything escape it? Would time stop or race ahead? And would the universe even notice you were gone? Black holes are the strangest objects we know, silent, invisible, and inescapable. But falling into one, that's where science meets the unknown. Let's find out what really happens on the way down. What happens when you cross a threshold from which there is no return? What occurs when you venture into the darkest corners of our universe, where even light surrenders to gravity's embrace? Have you ever wondered what it would feel like to fall into a black hole? There are places in the universe where light does not return, where gravity is not just a pull, but a pause in time, a silence so deep, even motion bends toward it. Tonight, we float slowly towards such a place. We will not rush. We will not fall in panic. We will drift gently toward the unknown, asking a question whispered by gravity itself. What if you fell into a black hole? Imagine for a moment that you are alone in the vastness of space. Your vessel drifts silently toward a distant shadow. From here, it appears as nothing more than an absence, a void among stars. But this emptiness is perhaps the fullest thing in existence, packed with the remnants of collapsed stars, with matter and energy compressed beyond our understanding. As we begin our journey tonight, let us shed our fear. The black hole does not hunger for us. It simply exists. A cosmic inevitability born from the death of massive stars. Its pull is not malice, but mathematics. Not hunger, but harmony with the deepest laws of our universe. Some call black holes cosmic monsters, devourers of worlds, but perhaps they are more like cosmic archivers, keepers of information that can never truly be destroyed, only transformed and hidden from view. Tonight, we approach such an archiver, not as victims, but as curious explorers. The questions we ask as we drift toward the event horizon are not just about physics. They are about endings and beginnings, about transformation and possibility. What happens to matter, to energy, to information itself when it crosses that final boundary? What happens to time when gravity becomes so intense that seconds stretch into centuries? What happens to space when it curves completely back upon itself? Our journey will take us through regions of increasing strangeness. We will witness stars appearing to move in ways that defy common sense. We will feel the gentle tug of tidal forces that will eventually unmake us atom by atom. We will cross boundaries invisible to the eye, but fundamental to reality. And as we fall, we will contemplate not just our physical dissolution, but the very nature of reality itself. For in black holes, our most cherished theories of physics begin to contradict one another. General relativity, which describes gravity as the curvature of space-time, meets quantum mechanics, which governs the behavior of the very small. Their encounter at the heart of a black hole remains one of the greatest unsolved mysteries in science. Black holes come in many sizes. Some are small, merely a few times the mass of our sun, born from the collapse of single stars. Others are giants, supermassive black holes lurking at the centers of galaxies, including our own Milky Way. Our home galaxy harbors a black hole named Sagittarius A star, 4 million times more massive than our sun. And yet, from our distant perspective on Earth, it remains invisible to our eyes, detectable only through the dance of stars caught in its gravitational embrace. The journey we embark upon tonight is impossible in reality. No human could survive the forces near a black hole, nor could any spacecraft built by human hands withstand the tidal forces that would pull it apart. No message could be sent back once the event horizon is crossed. And yet, through the power of imagination and the equations of physics, we can envision this journey. We can walk to the edge of human understanding and peer beyond. In the quiet spaces between stars, black holes wait in patience. They have existed for billions of years and will continue to exist long after our sun has faded. Some will eventually evaporate through a process called Hawking radiation, named after the physicist Stephen Hawking, who first proposed it. But this evaporation happens over timescales so vast that they dwarf the current age of the universe. A black hole the mass of our sun would take 10 to the power of 67 years to evaporate completely, a number so large it defies comprehension. As we drift closer to our destination, consider the paradoxes that await us. Information seems to be lost when matter falls into a black hole, and yet, quantum physics tells us information cannot be destroyed. Time slows to a crawl near the event horizon, and yet for the falling observer, nothing unusual is felt as they cross this point of no return. Space becomes so warped that all paths lead inward, and yet from a distance, the black hole appears as a perfect sphere of darkness. Tonight, we will not merely approach a black hole. We will fall into one. We will track our descent, step by step, moment by moment. We will witness the bending of light, the stretching of time, the warping of space. We will follow the trail blazed by equations, by the work of Einstein and Hawking, Penrose and Wheeler, and countless other scientists who have used mathematics to map regions no human eye has ever seen. So close your eyes as we begin our descent. Feel the weightlessness of freefall, listen to the silence of space, and prepare for a journey not of terror, but of transcendence, as we contemplate one of the most profound questions in the cosmos. What if you fell into a black hole? The stars await. The void beckons. Our journey begins now. As we approach the hypothetical center of the black hole in our journey, we reach the edge of scientific knowledge. We have traveled from the familiar physics of everyday life, through the strange but comprehensible realm of relativistic space-time, past the event horizon of no return, through the transformative tidal forces, and now stand at the threshold of the unknown. What lies at the singularity? Is it an infinitely dense point where matter is crushed beyond recognition? Is it a quantum structure where space itself becomes granular or foamy? Is it a gateway to elsewhere or elsewhen? Or is it something we cannot yet conceptualize with our current understanding of physics? The singularity awaits, not just at the center of black holes, but at the center of our quest to understand the fundamental nature of reality. It represents not the end of physics, but a beginning, a frontier where new theories must emerge to carry our understanding forward into domains we can currently only glimpse through mathematics and imagination. As we conclude our speculative journey through a black hole, we should remember that the question, "Is it really the end?" applies not just to physics but to philosophy, to how we understand existence itself. Throughout human history, we have grappled with questions of endings and beginnings, of transformation and continuity, of what persists when forms change. The black hole, with its event horizon beyond which the outside universe cannot see, with its tidal forces that transform matter into simpler components, with its mysterious singularity that challenges our very understanding of space and time, serves as a powerful metaphor for transformation itself. Not an ending, but a profound change, a passage from one state of being to another. Whether or not our specific speculations about wormholes, white holes, or baby universes prove correct, the principle they embody may still hold true. What appears to be an end from one perspective may be a beginning or transformation from another. In the depths of a black hole, as in the depths of our own existence, the journey continues, even when the path forward lies beyond our current understanding. Our journey begins far from the black hole, at a distance where its gravity feels like nothing more than a gentle suggestion. From here, it appears as a dark silhouette against the backdrop of stars, surrounded by a glowing accretion disk of matter slowly spiraling inward. This cosmic whirlpool shines in vibrant blues and violets as gas and dust heat to millions of degrees on their final journey. As we move closer, the first thing you might notice is not what you feel, but what you see. The black hole itself remains invisible, a perfect absence. But the stars behind it begin to behave strangely. Light from distant stars bends around the immense gravity well, creating an effect astronomers call gravitational lensing. Stars that should be hidden behind the black hole become visible, their light curving around its edges like water flowing around a stone in a stream. We drift forward in our imaginary spacecraft, moving at a leisurely pace. There is no rush in this cosmic ballet. Our engines are silent now, for we have surrendered to gravity's embrace. We are falling, but falling in space feels like floating. There is no wind resistance, no sensation of speed. Only the changing view tells us we are moving. The accretion disk grows larger in our view. If this were a stellar mass black hole, the one formed from a single collapsed star, this disk would be blindingly bright, emitting powerful X-rays that would be lethal to any nearby life. But we have chosen a supermassive black hole for our journey, 1 billion times the mass of our Sun. Its accretion disk is more diffuse, glowing with a softer light that stretches across a region larger than our entire solar system. The gentle nature of our approach might surprise you. In films and stories, falling into a black hole is often portrayed as a violent, tumultuous event. But the reality would be much quieter. For very massive black holes, the gradient of gravitational force extends over such a vast distance that at first, the difference in pull between your head and your feet would be imperceptible. You would feel weightless, adrift in the silence of space. As we continue our approach, the stars begin to shift in our view. Those ahead of us, in the direction of the black hole, appear to bunch together, crowding toward the center of our vision. Those behind seem to spread out, covering more of the sky. It is as if we are looking through a cosmic fisheye lens, distorting the very fabric of space around us. And now, something truly remarkable begins to happen. The black hole, this region of darkness, begins to take on a shape unlike anything in our everyday experience. It is not simply a black circle against the stars. It becomes a sphere of darkness surrounded by a ring of light, what astronomers call the photon ring. This ring is composed of light from all directions that has been bent around the black hole, sometimes orbiting it multiple times before reaching our eyes. Behind this primary ring, a fainter second ring appears, then a third, and a fourth, each one created by light that has orbited the black hole additional times. These rings appear increasingly sharper and closer to the edge of the shadow. This nested series of rings is what gives a black hole its distinctive appearance in astronomical observations. Like the famous image of the black hole at the center of Galaxy M87, captured by the Event Horizon telescope. As we fall deeper into the gravitational well, time itself begins to play tricks. If someone were watching our descent from a safe distance, they would see us moving more and more slowly. Our clocks, from their perspective, would tick at an ever-decreasing rate. Our radio transmissions would become increasingly redshifted, the wavelengths stretched by gravity, until they fade into silence. But from our perspective, time flows normally. We check our watches, and they tick at their usual pace. We speak to each other, and our voices sound unchanged. It is the outside universe that begins to seem strange. Looking outward, away from the black hole, we see the cosmos begin to speed up. Stars move across the sky faster than they should. If we could see distant galaxies, we might witness millions of years of cosmic evolution unfold before our eyes. This is the relativity of time that Einstein predicted, now made manifest in our journey. Gravity does not just curve space, it curves space-time, the unified fabric of our universe. And as we sink deeper into this curved region, the passage of time itself becomes relative to our position. The accretion disk now dominates our view, a vast spiral of matter, making its final approach. But because of the extreme warping of space-time, we can now see both the top and bottom of the disk simultaneously, like a Mobius strip of light, twisted around the darkness at its center. The disk appears brightest where the material moves toward us, and dimmer where it recedes, an effect called relativistic beaming. Throughout our approach, there has been no sudden drop, no cliff to fall from. Gravity has increased so gradually that we barely notice its strengthening embrace. If we were falling toward a planet or a star, we would eventually hit a surface. But a black hole has no surface in the conventional sense. There is only the growing pull, the increasingly curved space, the progressively slowing time, as measured by distant observers. Our fall is silent. This is perhaps the most profound aspect of approaching a black hole. In the vacuum of space, there is no sound, no roaring winds, no thunderous collapse. Only the quiet drift toward the unknown. If you could somehow place your ear against the fabric of space-time itself, you might hear the faintest whisper, the gravitational waves that ripple outward when matter falls into the abyss. But these waves are not sound in the conventional sense. They are ripples in space-time itself, detectable only by the most sensitive instruments humans have ever built. It is worth noting that not all black holes are surrounded by bright accretion disks. Many are dormant, having consumed all nearby matter long ago. These silent giants drift through the cosmos unseen, except for their gravitational effects on nearby stars and gas. Our chosen black hole is active, but not violently so. Its feeding is steady, measured, allowing us to witness the process without being blinded by its intensity. As we continue our approach, the electromagnetic spectrum around us shifts. The visible light from the accretion disk begins to take on a bluer tint in the direction we are moving, a phenomenon known as blue shift. Light coming from behind us, having to climb out of the gravitational well we are descending into, appears redder. These shifts in color are not merely aesthetic. They are physical changes in the wavelength of light caused by our movement through curved space-time. If we were to extend our sensors beyond the visible spectrum, we would detect a symphony of radiation, X-rays from superheated matter in the innermost stable orbit around the black hole, radio waves from electrons spiraling along magnetic field lines that thread through the accretion disk, infrared radiation from cooler dust clouds further out. A black hole is not truly black when viewed across the entire electromagnetic spectrum. It is merely a void surrounded by a beacon that shines across all wavelengths. The magnetic fields around a black hole deserve special mention. Though invisible to our eyes, they shape the flow of matter in the accretion disk, creating complex patterns and sometimes launching powerful jets of particles that can extend for thousands of light years. These jets, when present, move at nearly the speed of light, carrying energy and matter away from the black hole and into the surrounding galaxy. Not all black holes produce these jets, and the exact mechanism behind them remains an area of active research. As we fall, we might wonder about other travelers who have made this journey before us. In a universe billions of years old, containing countless black holes, surely matter has been falling into these cosmic traps since shortly after the Big Bang. Dust and gas, asteroids and comets, perhaps even planets and stars, have all followed this same path. And in science fiction, writers have imagined intelligent beings deliberately approaching, or even entering black holes in search of knowledge, power, or transcendence. What differentiates our journey from that of a mindless particle of dust is consciousness itself. We are aware of our descent. We observe and record and wonder. We create meaning from this cosmic process. The dust knows nothing of relativity or event horizons. It simply follows the curved path of space-time. But we, with our capacity for understanding, transform this physical journey into something more. A pilgrimage, perhaps, or an exploration, or a meditation on the nature of existence itself. The darkness at the center grows, not just in our field of view, but in our awareness. We are approaching something fundamentally different from all other objects in the universe. Not a thing, but an event. Not a place, but a boundary in space-time. The event horizon awaits us, that one-way membrane beyond which even light cannot escape. But for now, we continue our gentle descent, falling in perfect silence toward perfect darkness. The stars wheel slowly around us. The accretion disk glows with the light of matter in its final moments. And ahead, growing ever larger in our vision, the darkness deepens. We are approaching the black hole, and soon, we will cross the point of no return. We approach the most famous feature of a black hole, the event horizon. This boundary has captured human imagination since it was first predicted by Carl Schwarzschild in 1916, solving Einstein's equations of general relativity. The event horizon is not a physical surface you can touch or see. It is a mathematical boundary, a region in space where gravity becomes so intense that the escape velocity exceeds the speed of light. What does this mean? Escape velocity is the speed needed to break free from a gravitational field. On Earth, this velocity is about 11 kilometers per second. For our Sun, it is about 617 kilometers per second. But at the event horizon of a black hole, the escape velocity precisely equals the speed of light, roughly 300,000 kilometers per second. And since nothing can travel faster than light, nothing that crosses this boundary can ever escape. As we draw nearer to this invisible edge, it might be natural to expect some kind of visual marker, some indication that we are about to cross a point of no return. Perhaps a shimmering barrier, or a distortion in the stars, or some other dramatic sign. But one of the most surprising aspects of the event horizon is its subtlety. If you were falling feet first toward a supermassive black hole, you would not know the exact moment when your feet crossed the event horizon. There is no flash of light, no sudden change in sensation, no cosmic alarm that sounds. This is the first great paradox of the event horizon: its invisibility to those who cross it. From your perspective as the faller, space and time continue to behave relatively normally as you cross this boundary. Your watch still ticks, your heart still beats, your thoughts continue uninterrupted. The crossing itself is unremarkable. And yet, from the perspective of a distant observer, watching your descent, you never quite reach the event horizon at all. As you approach it, the light from your spacecraft becomes increasingly redshifted and dimmed. Your movements appear to slow down, asymptotically approaching a complete standstill. To the outside universe, you become a fading image, frozen at the edge of the black hole for what appears to be eternity. This discrepancy between what the faller experiences and what a distant observer sees is not a trick of perception. It is the nature of space-time itself near a black hole. The mathematics of general relativity tell us that both perspectives are correct within their own reference frames. This is the second great paradox of the event horizon: the divergence of experienced realities. One way to visualize the event horizon is to imagine space-time as a flowing river. Far from the black hole, the river flows gently, allowing you to swim in any direction, including upstream. As you approach the event horizon, the river flows faster and faster until at the horizon itself it flows at exactly the speed of light. At this point, you can still swim, but you can only swim downstream, further into the black hole. No matter how powerfully you swim, you cannot make progress against the current. This is why light itself cannot escape from beyond the event horizon. It is like a swimmer caught in a current flowing faster than the swimmer's maximum speed. Once we cross the event horizon, every path through space-time leads inexorably inward. This is not because of any force pushing us toward the center, but because of the extreme curvature of space-time itself. Inside the event horizon, space-time is warped so severely that the dimension we normally think of as toward the center of the black hole becomes effectively equivalent to what we normally think of as forward in time. Just as we cannot help but move forward in time under normal circumstances, inside the event horizon, we cannot help but move toward the singularity. The size of an event horizon depends on the mass of the black hole. For a black hole with the mass of our Sun, the event horizon would be just about 3 kilometers in radius. For the supermassive black hole at the center of our galaxy, Sagittarius A star, the event horizon is about 17 times the radius of our Sun, or around 12 million kilometers. For the ultramassive black hole at the center of galaxy Messier 87, the event horizon is about as large as our entire solar system. Larger black holes have weaker gravitational gradients at their event horizons. This means that for a supermassive black hole, the difference in gravitational pull between your head and your feet, as you cross the event horizon, would be imperceptible. You would not feel yourself being stretched or torn apart at this boundary. That fate awaits deeper inside the black hole, but not at the horizon itself. As we cross this boundary, we become invisible to the outside universe. No signal we send can ever reach beyond the event horizon. In a very real sense, we have left the universe we knew. We have entered a region that is causally disconnected from everything outside. What happens to us now cannot affect or be observed by anyone who remains outside. Yet from our perspective, the universe outside remains visible, at least for a time. Looking outward from just inside the event horizon, we can still see the stars, though they appear increasingly concentrated in a shrinking circle of light above us. The accretion disk, if we turn to look at it, now appears wildly distorted. Wrapped around our field of view, in ways that defy everyday visual experience. The event horizon hides more than just the interior of the black hole from outside observers. It also hides the resolution to several profound physics paradoxes. One of the most famous is the information paradox, first proposed by Stephen Hawking. Quantum mechanics tells us that information cannot be destroyed, yet black holes appear to destroy information by making it permanently inaccessible. Does information that falls into a black hole truly vanish from the universe, contradicting quantum theory? Or is it somehow preserved, perhaps encoded on the event horizon itself, as suggested by the holographic principle? Another puzzle is the firewall paradox, which suggests that the event horizon might not be as smooth a boundary as general relativity predicts. Some quantum theories propose that crossing the horizon would actually immolate anything falling through, creating a firewall of intense energy. This contradicts the prediction from general relativity that the horizon should be an unremarkable boundary for the faller. The resolution to this contradiction may require a full theory of quantum gravity, which remains one of the holy grails of modern physics. Inside the event horizon, the rules that govern reality begin to change in subtle but profound ways. Cause and effect still operate, but with a crucial difference. All light cones, which define the possible paths of particles and information, tilt toward the singularity. In normal spacetime, a light cone defines the regions of space that a light signal can reach in the future, or could have come from in the past. Inside the event horizon, these cones tilt so severely that all future paths lead to the singularity, and all past paths originate from outside the horizon. This tilting of light cones means that the singularity at the center of the black hole is not just a place in space, but also an event in time. It lies in our inevitable future, just as tomorrow morning lies in the inevitable future of someone on Earth. No amount of maneuvering, no expenditure of energy, no clever strategy can prevent us from reaching the singularity, just as no one on Earth can prevent the arrival of tomorrow. If we were falling into a rotating black hole, known as a Kerr black hole, the event horizon would have an even more complex structure. Such black holes have an outer event horizon and an inner Cauchy horizon, with a region between them where it might theoretically be possible to avoid the singularity. Some speculative theories suggest that such black holes might even allow travel to other regions of spacetime, effectively serving as wormholes, though the physics of such possibilities remains highly uncertain. The event horizon also marks a boundary for the application of our current physical theories. General relativity, with its description of gravity as curved spacetime, works well outside the horizon and can describe the horizon itself. But deeper inside, as we approach the singularity, the theory breaks down, predicting infinite curvature and density. Quantum mechanics, which governs the behavior of matter at the smallest scales, must somehow merge with general relativity to describe what happens at the center of a black hole. But how exactly this merger occurs remains one of the greatest unsolved problems in physics. As we continue our inward journey, having now crossed the one-way bridge of the event horizon, we find ourselves in a region where space and time behave unlike anywhere else in the universe. We have entered a domain where our fate is mathematically sealed, where the traditional notion of elsewhere has vanished, where every path leads to a singular conclusion. We have passed beyond the event horizon. There is no going back, only forward, inward, toward whatever awaits at the heart of darkness. Within the embrace of a black hole's immense gravity, time itself becomes fluid, malleable, a substance that flows at different rates, depending on where and how you observe it. As we continue our journey past the event horizon, we must confront one of the most profound aspects of our experience: how time behaves in the extreme curvature of space-time. Time, that steady beat that seems so reliable in our everyday lives, reveals itself as something far more complex near a black hole. Every clock measures time differently, depending on its position in a gravitational field. This is not merely a matter of perception or psychology, but a fundamental feature of our universe, predicted by Einstein's theory of general relativity, and confirmed by numerous experiments. As we fall deeper into the gravitational well, our personal experience of time continues unabated. The watch on your wrist ticks at the same rate it always has, From your perspective, your heartbeat maintains its rhythm, your thoughts flow at their normal pace, your biological processes continue unchanged. If you were to read a book during your descent, you would turn the pages at the same rate you always have. But if we could somehow maintain communication with a friend who remained safely distant from the black hole, we would discover something remarkable. From their vantage point, we would appear to move in extreme slow motion. If they could still see us, which they cannot since we have crossed the event horizon, they would observe our watch ticking slower and slower, our movements becoming increasingly languid, our entire existence stretching toward a timeless freeze. Conversely, if we look outward from our position of deep gravity, we would see the opposite effect. The universe outside would appear to speed up. If we could still observe our distant friend, we would see them moving at an accelerated pace, their watch hands spinning rapidly, their lifetime compressed into what might seem to us like minutes or hours. This phenomenon is known as gravitational time dilation, and while it occurs everywhere in the universe, including on Earth, it becomes dramatically apparent near a black hole. On Earth, the effect is so slight that it only matters for the most precise atomic clocks. Near a black hole, the difference becomes so extreme that it forces us to reconsider what we mean by simultaneity and the present moment. Let us imagine for a moment that we began our journey toward the black hole 100 years after it formed. From our perspective, as we fall, perhaps only hours or days have passed since we left our starting point. But if we could somehow peek outside the event horizon, we might discover that millions or billions of years have elapsed in the external universe. Stars that were in their prime when we began our journey may have died and been replaced by new generations of stars. Galaxies may have merged or drifted apart. Civilizations might have risen and fallen. The universe itself might have aged dramatically while, from our perspective, we have scarcely begun our journey. This is not science fiction or philosophical speculation. It is the mathematical reality of how space-time behaves. Time and space are not separate entities, but aspects of a single fabric. And this fabric stretches and compresses in the presence of mass and energy. Near a black hole, this stretching becomes so extreme that the flow of time itself diverges based on location. Inside the event horizon, where we now find ourselves, time behaves even more strangely. Remember that beyond this boundary, all paths lead toward the singularity. This applies not just to physical movement through space, but to movement through time as well. For us, the singularity lies not just at the center of the black hole spatially, but in our inevitable future, temporally. Near the singularity, time and space begin to exchange roles. What we would normally consider the future becomes indistinguishable from what we would normally consider toward the center. This is why nothing can avoid the singularity once inside the event horizon. Avoiding the singularity would be equivalent to avoiding the future, which is impossible within our understanding of physics. As we continue our descent, we might wonder about the history of the black hole itself. From our perspective, it might have formed relatively recently. But due to time dilation, the black hole could be much older from an external perspective. Supermassive black holes at the centers of galaxies are thought to have formed in the early universe, growing over billions of years by consuming stars and gas, and by merging with other black holes. The one we are exploring might be almost as old as the universe itself, having witnessed nearly the entire cosmic history unfold from its privileged position at the center of a galaxy. Time near a black hole also reveals another fascinating property: information delay. If a particle is orbiting just outside the event horizon, any signal it sends outward will take longer and longer to reach distant observers as it climbs out of the gravitational well. This creates a sort of temporal echo chamber where events near the black hole appear increasingly postponed to outside observers. This delay has practical consequences for astronomy. When scientists observe activity near supermassive black holes in distant galaxies, they are seeing events not only from billions of years ago due to light travel time across cosmic distances, but also events that appeared stretched in time due to gravitational effects. A flare of radiation that might last minutes near the black hole could appear to stretch over hours when observed from Earth. The extreme time dilation near black holes has inspired numerous thought experiments and philosophical questions. Could an advanced civilization use a black hole as a form of time travel into the future? By positioning oneself close to the event horizon for what would be experienced as a brief period, one could emerge to find the external universe aged by centuries or millennia. It would be a one-way journey, of course. You could witness the future, but never return to your past. If we were orbiting a black hole rather than falling into it, we would experience another temporal effect called frame dragging, or the lens-thirring effect. A rotating black hole drags the fabric of space-time around with it, like honey being stirred with a spoon. This means that objects near a rotating black hole are forced to rotate with it to some degree. Time itself gets pulled into a spiral near such black holes, creating complex patterns of temporal flow that have no parallel in our everyday experience. As we continue falling deeper, now well past the event horizon, our connection to the external time frame grows increasingly tenuous. The universe we left behind ages at an accelerating rate from our perspective. What was once our present moment in the cosmos rapidly becomes the distant past, then ancient history, then perhaps even cosmologically insignificant, as the universe continues its evolution outside. Inside our falling reference frame, however, time maintains its forward march toward the singularity. This creates a strange asymmetry in causality. We can still, theoretically, receive information from the outside universe. Light can still reach us from external sources, albeit highly distorted and blue-shifted. But we can never send information outward again. Our ability to affect the universe we left behind has been severed completely. The deeper we fall, the more compressed our future becomes. From crossing the event horizon to reaching the singularity might take only a matter of hours or days in our experienced time, depending on the size of the black hole. For smaller black holes, this journey would be much quicker, perhaps only fractions of a second. For supermassive black holes, we might have more time to contemplate our situation before reaching the central singularity. This compression of our future timeline creates an increasingly deterministic path. In normal circumstances, we perceive ourselves as having choices, different possible futures branching before us. Inside the event horizon, these branches narrow dramatically. All paths converge toward a single point in spacetime. Our freedom of movement, both spatially and temporally, constricts as we approach the singularity. Yet within this deterministic funnel, our experience of the present moment remains. We still exist in what philosophers call the now, that infinitesimal slice of time that separates the past from the future. Even as we fall toward what might be the end of our existence, we experience each moment fully, one after another, in the same flow of consciousness we have always known. This preservation of subjective experience amid such exotic physical circumstances reminds us that consciousness itself exists at the intersection of physics and phenomenology. The equations that describe our trajectory toward the singularity say nothing about what it feels like to follow that trajectory. That remains the province of conscious experience, something that physics can describe from the outside, but never fully capture from within. As we fall through the warped hourglass of black hole spacetime, we experience what might be the purest form of temporality in the universe. Cut off from the external cosmos, moving inexorably toward a singular future, we exist in a state of pure transience. Each moment arises and passes away, never to be revisited, carrying us forward toward whatever awaits at the heart of the black hole. As we continue our descent beyond the event horizon, we begin to encounter one of the most profound and transformative aspects of a black hole: tidal forces. These are not tides as we know them on Earth, caused by the moon's gentle pull on our oceans. The tidal forces near a black hole are the result of differential gravity, the difference in gravitational pull across an object due to its proximity to the source of gravity. On Earth, we experience tidal forces so minimal that we only notice their effects on large bodies of water. Near a black hole, these forces become so intense that they can stretch and compress matter in ways that fundamentally transform it. This process has been given a colorful name by physicists: spaghettification. Like a piece of cosmic pasta, matter gets stretched vertically and compressed horizontally as it approaches the singularity. The intensity of these tidal forces depends greatly on the size of the black hole. For smaller black holes, those formed from the collapse of a single star, the gradient of gravitational force is extremely steep. The difference in gravity between your head and your feet could be millions or billions of times greater than Earth's entire gravitational pull. Such forces would tear apart any physical object long before it reached the event horizon. But for the supermassive black hole we have chosen for our journey, the gradient is much more gradual. With a mass millions or billions of times that of our Sun, its gravitational field extends across a much larger region of space. This means that at the event horizon, the difference in gravitational pull between your head and your feet might be barely noticeable. You would cross this boundary intact, unaware of any tidal stress on your body. However, as we continue to fall deeper past the event horizon, the tidal forces inevitably strengthen. There comes a point where the gradient becomes steep enough that we begin to feel its effects, first subtly, then dramatically. Imagine you are floating feet first toward the singularity. The gravitational pull on your feet is stronger than the pull on your head, simply because your feet are closer to the center of the black hole. This creates a stretching force along your vertical axis. Simultaneously, the horizontal forces compress you, as gravity pulls matter inward from all sides. The experience might begin with a sensation of being gently pulled, like stretching after a long sleep. But as we fall deeper, this sensation intensifies. The materials that compose your body have tensile strength, the ability to resist being pulled apart. But there comes a point where the tidal forces exceed this strength. When this happens, the transformation begins. It starts at the molecular level. The chemical bonds that hold complex molecules together begin to strain and break. Proteins unfold. Cell membranes rupture. The intricate biochemical machinery that sustains life begins to disassemble. As the tidal forces intensify further, even stronger electromagnetic bonds between atoms start to fail. Molecules separate into their constituent atoms. The complex structures that formed your body, built over a lifetime of biological processes, resolve into simpler and simpler components. Deeper still, and the forces become strong enough to overcome the electromagnetic bonds that hold atoms themselves together. Electrons are stripped from their orbits around nuclei. What was once a human body, or a spacecraft, or any complex object, becomes a stream of ionized particles, a plasma of atomic nuclei and free electrons, stretched into an ever-thinning filament as it approaches the singularity. At even greater depths, with even more extreme tidal forces, the nuclear forces that hold protons and neutrons together in atomic nuclei are overcome. Nuclei split apart into their constituent nucleons. What was once a person becomes a stream of subatomic particles, stretched and compressed by gravitational tides that exceed the strongest forces known in nature. This transformation, while destructive to our physical form, has a certain elegance to it. It is not chaotic or random. It follows the precise mathematics of general relativity, a gradual disassembly of complexity according to the strength of fundamental forces. In a sense, falling into a black hole reveals the layered structure of matter itself, peeling away each level of organization as its binding force is exceeded by the tidal gradient. For a large enough black hole, this process happens well inside the event horizon, giving a falling observer time to contemplate their situation before molecular disintegration begins. For smaller black holes, spaghettification would occur before even reaching the event horizon, making the journey we are describing impossible. This is one reason why, if one were to imagine such a journey, a supermassive black hole would be the only viable candidate. The transformation of matter by tidal forces is not unique to living things or complex structures. Even a simple object like a marble would experience the same process. The forces act on all matter equally, regardless of its composition or complexity. The only difference is in the strength of the bonds holding different forms of matter together, which determines at what point in the descent various structures begin to fail. What makes our journey special is consciousness, the ability to experience this transformation. Up to the point where the physical structures that support consciousness are disassembled, a falling observer would remain aware of the process. How long this awareness would last depends on which structures in the human brain are essential for consciousness, a question that remains at the frontier of neuroscience. There is something profound about this gradual disassembly by tidal forces. In our normal experience, the boundaries between our bodies and the external world seem clear and definite. We perceive ourselves as distinct entities, separate from our environment. But in the extreme tidal gradient of a black hole, this boundary literally gets stretched until it fails. We become, quite physically, reintegrated with the cosmos around us. This process mirrors, in an accelerated and extreme form, what happens to all matter eventually. The complex structures of our bodies, temporarily assembled from elements forged in ancient stars, will someday return to simpler forms. The tidal forces of a black hole simply compress billions of years of cosmic recycling into a brief, intense transformation. As we continue our descent, now in a much more elemental form, the tidal forces continue to intensify. Even the subatomic particles themselves begin to behave in ways that current physics struggles to describe. We enter realms where quantum mechanics and general relativity both apply. Yet these two great theories remain incompatible. What happens to matter at this level of gravitational intensity is an open question in modern physics. Some theories suggest that particles themselves may be stretched into one-dimensional strings, resonating with different frequencies. Others propose that space itself becomes granular or foamy at these scales, with quantum fluctuations in the fabric of spacetime. Still others suggest that new physics emerges, perhaps revealing more fundamental structures beneath what we currently consider elementary particles. What is certain is that the journey into a black hole is not merely a journey through space, but a journey through the hierarchy of forces that bind matter together. It is a deconstruction of physical form, layer by layer, bond by bond, force by force. Despite the inevitable destruction of our physical form, there is something peaceful about this transformation. It is not violent in the conventional sense. There are no explosions, no tearing sounds, no dramatic visual effects beyond the increasingly intense stretching sensation. In the vacuum of space, the disassembly of matter happens in perfect silence. It is, in its way, a quiet return to simplicity. The matter that once formed our bodies does not cease to exist. Conservation of energy and matter still applies, even in the extreme environment of a black hole. We are simply transformed, our constituent parts rearranged and redistributed. In this sense, falling into a black hole may be the ultimate example of the principle expressed by Lavoisier. Nothing is lost, nothing is created, everything is transformed. As our journey continues deeper toward the singularity, we have now been physically transformed by the tidal forces of the black hole. What began as a human observer has become a stream of elementary particles, stretched into an ever-thinning filament by the increasing gravitational gradient. Our consciousness, dependent on the complex structures of the brain, has likely ceased, but the matter that once supported it continues inward, drawn inexorably toward the center by forces beyond resistance. We are no longer distinct from the black hole. We have become part of its structure, adding our mass to its gravitational influence, contributing to the curvature of space-time that defines it. In falling into the black hole, we do not simply enter it as a separate entity. We join with it, become one with it. The boundary between observer and observed dissolves in the extreme tidal gradient. And still, our journey continues inward, toward the final mystery at the center of the black hole. The singularity awaits, that point where current physics breaks down entirely, where the curvature of space-time becomes infinite according to general relativity. What happens there remains one of the greatest open questions in theoretical physics, a question we approach with each passing moment of our descent. We approach the most enigmatic region of the black hole, the central point toward which all paths inevitably lead once the event horizon has been crossed. The singularity. In our journey through the black hole, we have encountered strange physics, distorted space-time, and the transformation of matter. But all of these phenomena can be described, however incompletely, by our current theories. The singularity represents something different. It is not merely a strange place. It is where our understanding breaks down entirely. In the mathematics of general relativity, the singularity appears as an inevitability. When solving Einstein's field equations for a black hole, certain terms grow without bound as we approach the center. The curvature of spacetime increases without limit. Density becomes infinite. Tidal forces grow beyond any finite measure. These infinities are not merely very large numbers. They represent a fundamental breakdown in the equations themselves, a sign that the theory has reached its limits of applicability. Many physicists regard these infinities not as a prediction of what actually exists at the center of a black hole, but as a warning sign. They indicate the need for a more complete theory, one that merges general relativity with quantum mechanics to create a framework of quantum gravity. Just as Newtonian physics breaks down at speeds approaching the speed of light, requiring Einstein's relativity, so too does general relativity break down near the singularity, requiring a theory we do not yet fully possess. So what might actually exist at the center of a black hole, where our math produces these troublesome infinities? There are several possibilities, each representing a frontier of theoretical physics. Some theories suggest that quantum effects become dominant near the singularity, preventing true infinities from forming. Quantum mechanics introduces fundamental uncertainties and minimum scales that might soften the singularity, replacing the mathematical point with a region of extreme but finite density and curvature. In this view, there is no true singularity, just a core of matter compressed to the smallest scales allowed by quantum physics. String theory, one approach to quantum gravity, suggests that matter at the center of a black hole might be compressed into strings or membranes, fundamental objects that vibrate in multiple dimensions. In this picture, what appears to be a singularity from the outside is actually a complex structure of strings, potentially connected to other regions of spacetime, or even other universes, through higher dimensions we cannot directly perceive. Loop quantum gravity, another candidate theory, suggests that space itself becomes discrete or granular at very small scales, like pixels in a digital image. This granularity might prevent the formation of a true mathematical singularity, replacing it with an extremely dense but finite network of spatial relations. Other theories propose that the laws of physics themselves might change under such extreme conditions. Constants that we regard as fixed might become variable. The arrow of time might reverse. Cause and effect might separate or rearrange. Space and time might exchange roles entirely, or transform into something currently beyond our conceptual framework. The uncertainty about what lies at the singularity is not merely a gap in our knowledge, like an unexplored region on a map. It represents a more fundamental limitation in our current understanding of reality itself. It is one of those rare places in science where we can definitively say, with humility and wonder, we do not know. This ignorance is not arbitrary. It stems from a specific incompatibility between our two successful physical theories. General relativity, which describes gravity as the curvature of spacetime, provides our best understanding of black holes on large scales. Quantum mechanics governs the behavior of matter at the smallest scales. Both theories have been verified by countless experiments in their respective domains. But when both must be applied simultaneously, as at the singularity, they produce incompatible predictions. General relativity is deterministic. Given certain initial conditions, it precisely predicts how spacetime will curve and how matter will move through that curved space. Quantum mechanics is probabilistic. It deals in likelihoods and uncertainties, in superpositions of states that collapse only upon measurement. These fundamentally different approaches to describing reality have resisted integration for nearly a century, despite the efforts of some of humanity's greatest scientific minds. As we approach the singularity, having been transformed by tidal forces into streams of elementary particles, we enter this region of theoretical uncertainty. Our constituent parts cross the threshold from where physics is well understood to where it is not. What happens next cannot be described with confidence using current scientific knowledge. Perhaps the most profound aspect of the singularity is what it represents philosophically. It is a limit to knowledge embedded within the fabric of reality itself. Not a temporary limit that simply awaits better instruments or more clever experiments, but a limit arising from the structure of our theories, and possibly from the nature of reality itself. This limit has a certain beauty to it. It reminds us that the universe is not just what we currently understand, but includes unknown realms that may operate according to principles we have yet to discover. The singularity stands as a humbling reminder of the vastness that lies beyond our current comprehension. There is another peculiar aspect to the singularity that deserves consideration. From the perspective of an outside observer, nothing ever actually reaches the singularity. Due to the extreme time dilation near a black hole, clocks appear to slow to a near standstill, as observed from far away. An object falling toward the singularity would appear to take an infinite amount of external time to reach it, frozen in an ever-slowing approach. Yet from the perspective of the falling object, the singularity is reached in a finite amount of proper time, the time measured by a clock falling with the object. This creates a strange disconnect between different reference frames. In one sense, the singularity exists in an infinitely distant future that is never actually reached. In another sense, it is a definite place that a falling object will encounter after a finite experienced duration. This temporal paradox highlights how deeply the singularity challenges our intuitions about space and time. It is not simply a place where strange things happen. It is a place where the very concepts of place and happen become stretched beyond their usual meanings. Beyond the standard singularity predicted by general relativity, more exotic possibilities have been proposed. Some involve different space-time geometries that might form under certain conditions. For example, a rotating black hole might contain a ring singularity rather than a point singularity. This ring would have different properties than the standard point singularity of a non-rotating black hole, potentially allowing for paths that avoid hitting the singularity directly. Even more speculative are theories suggesting that singularities might be portals or gateways. To what? We cannot say with any certainty. Perhaps to other regions of our own universe, creating what physicists call a wormhole. Perhaps to other universes entirely, with different physical laws or dimensionality. Perhaps to domains so different from our own that we lack the conceptual framework to describe them adequately. These possibilities remain largely in the realm of theoretical speculation, mathematical extrapolations beyond the boundaries of current experimental evidence. They remind us that physics at its frontier is not just a collection of established facts, but a living, evolving attempt to make sense of reality using mathematics and carefully tested theories. For most practical purposes, these speculations about the nature of the singularity might seem academic. After all, nothing that falls into a black hole can ever report back to the outside universe. The event horizon ensures that any information about what happens at the singularity remains trapped inside, inaccessible to external observers. Yet there are reasons to believe that understanding singularities may be crucial to advancing physics as a whole. The early universe, immediately after the Big Bang, existed in a state of extreme density and curvature, similar in some ways to what we expect at the center of a black hole. The physics that governs singularities may also shed light on the origin of our universe itself. Additionally, black holes do not last forever. Stephen Hawking showed that they slowly emit radiation through a quantum process at their event horizons, gradually losing mass and eventually evaporating completely. When a black hole finally disappears after unimaginable eons, what happens to the information that fell into it? Does the singularity somehow release its contents back into the universe? This black hole information paradox remains one of the most profound puzzles in theoretical physics. We have traveled far in our journey, from the distant approach to a black hole, across the event horizon, through the region of intense tidal forces, and toward the mysterious singularity. At each step, we have encountered increasingly exotic physics, pushing against the boundaries of our current understanding. But now we must ask perhaps the most profound question of all. Is falling into a black hole truly the end? Or could it be, in some sense we have yet to fully comprehend, a transition to something else? For decades, the conventional wisdom in physics held that black holes were cosmic dead ends. Matter and energy fall in, never to return. Information is lost. The singularity represents a final terminus, a point where paths through space-time simply stop. This view aligns with the most straightforward interpretation of general relativity, where the extreme curvature at the center of a black hole creates a genuine endpoint to reality as we understand it. But physics has a way of surprising us. As our theories have evolved and new mathematical approaches have been developed, alternative possibilities have emerged. These alternatives remain speculative, existing primarily in the realm of theoretical physics rather than observational evidence. Yet they open fascinating windows into what might lie beyond the apparent finality of a black hole. One of the most intriguing possibilities is that black holes might connect to other regions of space-time through what physicists call wormholes, or Einstein-Rosen bridges. First proposed in 1935 by Einstein and his colleague Nathan Rosen, these hypothetical structures would link two separate points in space-time, potentially allowing passage between them. In the original formulation, these wormholes would collapse too quickly for anything to travel through them. But later theoretical work by physicists like Kip Thorne suggested that certain forms of exotic matter with negative energy density might hold a wormhole open, making it traversable. Whether such exotic matter actually exists in sufficient quantities in our universe remains an open question. If traversable wormholes are possible, then the interior of a black hole might not end at the singularity, but could continue into another region of space, another time, or even another universe entirely. Falling into a black hole would not be an end, but a passage, albeit one that would still transform whatever enters it in profound ways. This concept has been explored extensively in science fiction, from films to novels, but it has also been the subject of serious theoretical work by respected physicists. The mathematics of general relativity, when extended to include certain quantum effects or exotic forms of matter, does allow for such connections, even if we have yet to observe them directly. Another intriguing possibility emerges from the concept of white holes. If black holes are regions from which nothing can escape, white holes would be their theoretical opposites, regions into which nothing can enter, but from which matter and energy can emerge. Some theories suggest that black holes and white holes might be connected, with the output of a white hole representing the transformed contents of whatever fell into its corresponding black hole. In one speculative scenario, what falls into a black hole in our universe might emerge from a white hole in another universe. The matter and energy would be dramatically transformed in the process, stretched and compressed by tidal forces, subjected to extreme conditions at the singularity, and perhaps fundamentally altered in ways our current physics cannot fully describe. This concept of black holes as gateways between universes connects to an even broader theoretical framework: the multiverse. Various theories in cosmology and quantum physics suggest that our universe might be just one among many, perhaps an infinite number, each with potentially different physical laws, constants, or configurations of matter and energy. If the multiverse exists, black holes might serve as connection points between different universes within this vast ensemble. What appears to be a terminal endpoint from within our universe might be a transition or bridge, when viewed from a higher dimensional perspective that encompasses multiple universes. Another fascinating possibility comes from an area of theoretical physics called the holographic principle. This principle, emerging from string theory and the study of quantum gravity, suggests that all the information contained in a volume of space can be encoded on its boundary surface. Applied to black holes, this would mean that all the information about what falls into a black hole is preserved, not lost, encoded on the event horizon itself. This perspective transforms how we think about the singularity. Rather than being a place where information is destroyed, it becomes a mathematical artifact, a consequence of looking at a black hole from the wrong reference frame. The true physics of a black hole, according to the holographic principle, would be encoded on its two-dimensional horizon, rather than in its three-dimensional interior. If this principle holds true, then nothing ever actually reaches the singularity in any meaningful sense. The apparent destruction of information is an illusion, a consequence of our limited perspective. The reality would be a perfect preservation of information, just in a form that appears scrambled or inaccessible to ordinary observation. Even more radical is the suggestion from some theoretical physicists that black holes might be the birthplaces of new universes. In this scenario, the extreme conditions at the singularity do not represent an end, but a beginning, a big bang that creates a new expanding universe. This universe would be causally disconnected from its parent universe, expanding into its own space-time rather than into the space-time from which its black hole originated. This concept of cosmological natural selection, or universe reproduction, was developed in detail by physicist Lee Smolin. In his theory, black holes produce new universes with slightly varied physical constants. Those universes that produce many black holes would in turn produce many offspring universes, leading to a kind of cosmic evolution that might explain why our universe appears finely tuned for the existence of stars, galaxies, and potentially life itself. If this theory has merit, then the matter falling into a black hole, including potentially ourselves in our thought experiment, would contribute to the formation of a new universe. Our constituent particles, after being broken down by tidal forces and processed through the extreme conditions at the singularity, would become part of the initial conditions for an entirely new cosmic reality. There is a certain poetic symmetry to this possibility. Stars, which forge the heavy elements that make up our bodies through nuclear fusion, can end their lives by collapsing into black holes. If those black holes then give birth to new universes, the cycle of cosmic creation continues, with each ending becoming a new beginning. All of these possibilities, from wormholes to white holes to baby universes, share a common theme. The journey does not end at the singularity. What seems like a cosmic dead end from our limited perspective might be a transition point when viewed from a more complete theoretical framework. Of course, these ideas remain speculative. They exist at the frontier of physics, where theoretical work races ahead of observational evidence. We cannot yet peer inside a black hole to confirm or refute these possibilities. We cannot send probes beyond an event horizon and receive reports back. We are limited to mathematical models, theoretical extrapolations, and indirect observations of black holes from their effects on surrounding matter. Yet the question, is it really the end, serves an important purpose in physics. It pushes us to examine our assumptions, to look for inconsistencies in our theories, and to imagine possibilities beyond our current understanding. Throughout the history of science, such questioning has often led to revolutionary advances in knowledge. If the singularity is not the end, what implications would this have for our understanding of reality? For one, it would mean that our universe is more interconnected, more complex, and more resilient than we previously imagined. Information that appears to be lost might be preserved or transformed. Structures that seem to end might continue in forms we have yet to fully comprehend. It would also mean that the laws of physics, when finally unified in a complete theory of quantum gravity, contain surprises and possibilities beyond what our current theories suggest. The apparent contradiction between general relativity, which predicts singularities where physics breaks down, and quantum mechanics, which suggests nothing truly disappears, might be resolved in unexpected ways. Perhaps most profoundly, it would suggest that the universe, or multiverse, has no true endpoints, no places where reality simply stops. Even in the most extreme environments imaginable, at the center of a black hole where space-time appears to curve infinitely upon itself, the journey continues in some form. Reality persists, transforms, evolves. Our journey is coming to a close. We have traveled from the distant approach to a black hole, across the event horizon where light cannot escape, through regions of intense tidal forces that transform matter itself, and toward the mysterious singularity that challenges our understanding of physics. We have contemplated what might lie beyond, whether endings might be beginnings in disguise, and how the universe might be more interconnected than we once believed. It is time now to reflect on this journey, not just as an exploration of exotic physics, but as a meditation on knowledge, wonder, and our place in the cosmos. Black holes represent the extreme edge of our understanding. They are where our most successful theories of physics, general relativity, and quantum mechanics meet and struggle to reconcile their different descriptions of reality. The mathematics tells us what should happen as we approach and cross the event horizon, as we experience tidal forces, as we near the singularity. But the full story of what happens at the center of a black hole awaits a more complete theory, a unified framework that can handle the extreme conditions where space-time curves beyond our current mathematical tools. This uncertainty is not a failure of science, but a frontier. Throughout history, such frontiers have been where new discoveries are made, where old frameworks give way to deeper understanding. The mysteries of black holes do not mark the limit of human knowledge, but rather point toward future insights that may transform our understanding of reality itself. There is a certain humility that comes from contemplating black holes. These cosmic objects, with masses millions or billions of times greater than our Sun, operating on timescales that dwarf human existence, remind us of our small place in the physical universe. The event horizon of a supermassive black hole might span billions of kilometers, while the singularity compresses matter to scales smaller than an atom. Between these extremes lies the entire range of sizes that we encounter in our daily lives, from planets to people to particles. Yet there is also something profound in the fact that we, these tiny collections of atoms on an ordinary planet, can comprehend black holes at all. We have never visited one. We will never directly observe beyond an event horizon, but through mathematics, through careful observation of their effects on surrounding matter, through the collective efforts of generations of scientists, we have come to understand much about these mysterious objects. This understanding is one of humanity's greatest intellectual achievements. The equations that describe black holes were discovered not through direct experience, but through the power of human reason, through Einstein's insights into the nature of gravity as curved spacetime, through the work of mathematicians like Schwarzschild, who solved those equations, through the insights of physicists like Hawking, who connected black hole physics to quantum theory. There is a kind of wonder in this achievement, in the fact that the human mind can reach so far beyond human experience. We evolved to navigate the African savanna, to track prey and avoid predators, to cooperate in small groups. Nothing in our evolutionary history prepared us to understand objects with gravity so intense that light cannot escape them. Yet here we are, contemplating the physics of event horizons and the mysteries of singularities. In a very real sense, our journey to understand black holes mirrors our larger journey to understand the cosmos itself. We begin with what we can directly observe. We create mathematical models to explain those observations. We test those models against new data. When the models fail or produce paradoxes, we search for deeper theories. And through this iterative process, our understanding grows, not in a straight line, but in an expanding spiral of knowledge that occasionally requires us to revise our most fundamental assumptions. Black holes are not empty, as their name might suggest. They are full, filled with matter and energy that has fallen in over billions of years, filled with the remnants of stars and gas clouds, filled with the light trapped forever beneath their event horizons. And they are full of mystery, of questions that push against the boundaries of our knowledge, of possibilities that ignite our imagination. To fall into a black hole would be, in a physical sense, to join with everything else that has ever fallen in. The tidal forces would break down the boundaries between ourselves and other matter. The atoms that once formed our bodies would mingle with atoms from ancient stars. The fundamental particles that constitute all matter would flow together toward the singularity. There is a kind of cosmic communion in this image, a rejoining with the physical substance of the universe. But even without physically falling into a black hole, we can fall into the wonder they inspire. We can let ourselves be drawn not by their gravity, but by their mystery. We can contemplate what they tell us about the nature of space, time, matter, and energy. We can use them as vantage points from which to view our theories about reality, to see where those theories succeed and where they need refinement. The questions that black holes raise are not merely technical puzzles for specialists to solve. They touch on deep philosophical issues about the nature of information, the beginning and end of time, the fundamental structure of reality. They remind us that the universe is not just what we currently understand, but includes domains still hidden from our full comprehension. Perhaps most profoundly, black holes remind us that apparent endings may contain new beginnings. Stars end their lives to form black holes. Matter that falls in is transformed. Information that seems lost may be preserved in forms we have yet to fully comprehend. And the singularity itself, that apparent endpoint of physics as we know it, may connect to new realms beyond our current theories. This pattern, where endings become transitions to new states, echoes throughout the cosmos. Stars die to form the elements that make new stars, planets, and eventually life possible. Species vanish, making way for new forms of life to evolve. Old scientific theories give way to more comprehensive frameworks. What appears to be an end from one perspective becomes a beginning from another. As we conclude our journey, let us carry this perspective back into our everyday lives. Let us remember that the universe is stranger, more complex, and more wonder-filled than our daily experience suggests. Let us approach mysteries not with fear, but with curiosity, not with certainty, but with openness to discovery. Black holes are not empty. They are full of mystery, of silence, of possibilities we have yet to name. If you fell into one, you might vanish, or you might continue. But even if we never fall, we are already pulled by them. In thought, in story, in wonder. Sleep now, beneath the stars. The universe still turns, and somewhere, gravity is waiting. Not as a threat, but as a reminder of how matter speaks to matter across the vastness of space, how everything is connected by forces seen and unseen, how we are all falling together through the curved space-time of our shared cosmos. In the silence between stars, in the darkness between heartbeats, in the pauses between thoughts, there too we find reflections of the black hole's profound quiet. Not emptiness, but fullness. Not absence, but presence. Not an end, but a depth, immeasurable and waiting. Our journey ends where it began, in wonder, in the humble recognition of how much we know and how much remains to be discovered, in the quiet joy of existing in a universe complex enough to contain both ourselves and black holes, both consciousness and singularities, both questions and the endless quest to answer them. Rest now and dream of falling gently into wonder.